Okay, so in today's lecture, we are going to talk about networking concepts as they relate to both a Unix-like monolithic kernel such as Linux and Minix. So last time, if you remember, we talked about file systems, file server processes, and so on. And we are done with that part of the course. And today we are going to switch gears and talk about networking concepts. So this is also the last major topic as far as Minix is concerned. And in the next few classes, we are going to switch back to Linux and talk about how many of the concepts we have covered in the past few classes, memory management, I/O, and so on, relate to Linux. So coming back to today's class, we are going to talk about very quickly network protocol concepts at a very high level. Then I'm going to talk a little bit about Unix networking, specifically from the perspective of the Linux OS. And then I'm going to talk about how many of the concepts are implemented in the Minix microkernel. So first, let's talk a little bit about networking protocols or communication protocols. So what is a protocol? A protocol is a set of rules for communication that are agreed to by the parties involved in that communication. So that's a very general concept. Protocols are used in many different domains that go beyond computer science. But in the context of networking, protocols are used for communication over a network. And we have something called a protocol stack, which is how the networking subsystem is organized into layers. An example of a protocol stack is shown in this figure, where we have essentially three machines, A, B, and C, that are shown. And A and B are the sending machine and the receiving machine, the sender and the receiver, host or the source and the destination, as they are called. And B is an intermediate node, also called a router. Okay. So you will see that each of these machines has an OS that runs a network protocol stack, and the network subsystem is organized using layers. So going back to the very first classes, if you remember, I talked about using a layered architecture, and I also said that this architecture is especially common in a networking subsystem. And so this figure illustrates that concept, and you will see this protocol stack here is called the ISO or the OSI stack, and you will see that this stack actually has 7 different layers, starting from the physical layer, the data link layer, the network layer, transport layer, session layer, presentation layer, and application layer. Okay. So we'll talk about some of these key layers in the next slide, but as far as this protocol stack is concerned, a few concepts that apply to the layered architecture apply. Each layer presents an interface to the layer above it using the interfaces provided by the layer below it. So what that means is each layer in this protocol stack can only communicate with the layer above and the layer below it. Okay. So the network layer, for example, has to use the functions provided by the data link layer and provide a network protocol abstraction to the transport layer, for example. Okay. Now, the protocol stack here shows an idealized approach of 7 different layers. But not every protocol stack has to implement all of them. They will have some of the key layers, but not necessarily all of them. So that's something to keep in mind, and I'll talk about the layers that are present in the TCP/IP protocol stack in a moment. But let me also say something about node B that sits between node A and C here. Okay. So node B is an intermediary node that is in this case is called a router. Okay. So the way network protocols work is they assume that when you send a message from the source to the destination, that message is going to be sent in terms of one or more network packets. These packets are going to be sent over the network, but because there may not be a direct connection between A and C, a direct network connection between A and C, that packet has to go through intermediate nodes that are called routers. The goal of routers is simply to take incoming packets look at the source address and the destination address, which is going to be present in the packet, and then decide which node to send it next. So, although in this figure we have only one router sitting between A and C, typically you may have more than one routers involved in forwarding that packet, so that it eventually gets to its destination node, which in this case is C. Okay. So, let us look quickly at the TCP/IP protocol stack, and what you will see here is that you have the data link layer, the network layer and the transport layer, but some of those other layers that were present, the session layer and the presentation layer, are not really present in the TCP/IP protocol stack. What that means is any functionality that was necessary in the session layer and the presentation layer are all done by the application process itself. Okay. So, let us now look at a little more detail. I am going to start at the top. Okay, at the very top, you have an application process that might be trying to communicate. Let us say it is a browser process. Okay, if it is a browser process, it is going to use an application layer protocol for communication, which in this case is going to be the HTTP protocol. Okay. So, that is our application layer protocol. At the other end, which is not shown here, there will be another process. In this case, that is going to be a web server. So, the web browser at the client and the web server on the server machine are the two application layer processes that are communicating using HTTP. Okay. Now, as far as the application layer processes are concerned, they do not actually care about how the HTTP communication takes place in terms of the transport and the network and the data link layer. They just understand HTTP, and when when you send a message, you construct an HTTP message. At the other end, when you receive a message, you receive an HTTP message, and you understand what the fields of the message are and so on. So in some sense, each layer is implementing a protocol that is somehow agnostic of the protocols that are underneath. So now the browser wants to send now a packet to this web server. So, it is going to construct an HTTP packet, and it is going to hand it to the next layer below it. Okay. Now, suppose you wanted this message to go securely over the network, because maybe you are communicating with a web server that represents your bank website. So, in this case, you might actually have a session layer. Although that is not a separate layer in the TCP/IP context, it is a library that may be attached to the application process. So, in this case, the session layer might provide us with SSL or secure encryption. So, all of the HTTP packets are encrypted by the session layer and the sender. They are sent encrypted over the network, and at the other end, you basically receive the packet at the session layer, you decrypt it, and then you hand back the original message to the server process. So, in this case, the presence of the session layer is not necessarily known to the application process. It is just sending and receive HTTP messages, but you can use this layer to provide encryption functionality, for example. So when you have HTTPS messages, they are automatically constructing HTTP messages that use the SSL encryption layer below it. Now, as that message percolates down the protocol stack, it is going to arrive next at the transport layer. So, in the TCP/IP context, that which incidentally stands for TCP stands for Transmission Control Protocol, and IP stands for Internet Protocol. So, in the TCP/IP protocol stack, TCP is the protocol that is implementing the transport layer functionality, and IP is the protocol that implements the network layer functionality. Okay. So, TCP and its sister protocol, which is called UDP, implement transport layer functions. TCP is an end-to-end protocol, which means it is responsible for end-to-end communication at the source and the destination in terms of handling lost packets. If you send a packet and it gets lost over the network, TCP is responsible for detecting losses and retransmission. It is responsible for rate control, which means it determines at what rate or what speed should the packets be sent, because network conditions can change over time and so on. TCP sister protocol UDP also provides transport layer functions, but it is a much simpler protocol in that it does not provide functions such as rate control or error or detecting lost packets and so on. So you just, in case of when you're using UDP, you can simply start sending packets. If they get lost, UDP is not going to handle those losses. They have to be dealt with at the application layer and so on. Okay. So in any case, the HTTP message now, let's say, which is encrypted, arrives at the TCP layer. The TCP layer adds some headers and then hands it to the IP layer. Okay. The IP layer, which is the network layer, is responsible for bulk of the work in terms of sending it out and forwarding it over the network on a hop-by-hop communication. So IP, or the network layer, does hop-by-hop communication, whereas transport layers always does end-to-end communication. So in this case, the IP protocol is going to add headers such as the source address, the destination address, which is the IP address of the web server, and so on, and then hand it to the data link layer, which in this case is shown as IEEE 802.x. So that's a standard, IEEE standard, and there's a family of protocols called 802.x. 802.3 stands for wired Ethernet, 802.11 stands for Wi-Fi, and so on. So that's a family of protocols that implement the data link layer functionality. So the IP message is then taken by the data link layer, you add a header to it, and then you send it over the physical layer, which is the actual medium. So this could be the wire, or this could be, in case of wired Ethernet, or it could be the in case of wireless, you just send it over the air. So you essentially have a wireless channel between, in that case, wireless access point and the next access point of the router. So that's very briefly the TCP/IP protocol stack. Now, if you've taken a course in networking, you would have gone into all of this in a lot more detail. In this class, we don't need to go into the details of networking. We just need to know that there's a protocol stack, and we are going to actually look at how the OS is going to implement this protocol stack. Right? Now, because the user process implements most of these functions, such as HTTP, as well as all kinds of other protocols such as FTP and SMTP and whatnot. We are not going to look at the user level protocols for today's lecture. Instead, we are going to focus on the data link layer, which for the purposes of today's class is going to be Ethernet or wired Ethernet, the network layer, which is going to be IP, and the transport layer, which is going to be both TCP and UDP. We are going to see how these three layers are actually implemented in an OS kernel. Okay. Now, typically, most Unix-like operating system provide an abstraction to user processes for using the TCP/IP protocol stack, and that abstraction is called a network socket. Think of sockets as an abstraction that is similar to files. The file system provides a file abstraction. You can read or write to files, and then that data is stored on a disk. The network subsystem provides a socket abstraction, and you can read or write to this socket abstraction, and then that data is going to be sent over a network. Just as the file system stores that data to a file, when you write to a file descriptor, when you write to a socket descriptor, that data is actually sent over a network, or you can receive the data from a socket over a network. So this abstraction of sockets is what is actually used for communication using the TCP/IP protocol, but the abstraction is general, and we'll see that the same abstraction can be used for other protocol families, not just the TCP/IP protocol stack. Okay. The picture here shows a very simple client and a server that are communicating over a network using socket communication, and each box represents a system call. Well, not a system call, but it's a POSIX socket call that is used to enable this communication. So initially, both the client and the server have to create a socket, which is two endpoints that are going to be used for communication. The server is then going to bind that socket to a port number. In the networking context, every socket has a port number. So for example, web servers listen on port 80, network port 80. When you do SSH, you communicate to port 22. So ports are essentially addresses on a machine that represent endpoints. The IP address allows you to address the machine, and port numbers allow you to communicate to a specific endpoint, which is where a process is listening to. Because there may be multiple processes that are involved in communication. Each of them is given an ID, which is called a port number. That is their address on that machine for communication, or that's their endpoint address for communication. So the server has to bind to a port number to listen on that port, which is its local address or the local endpoint on that machine. And then it starts listening, which means that it is waiting to receive packets, and then it can essentially do accept, which is where it's actually waiting to receive a message. Now the client, on the other hand, also has to open a socket, as you can see in this picture, and then to communicate with the client server, it basically just does a connect. At that point, the connect on the client and the accept on the server are both going to establish a TCP/IP connection between the two machines. Till this point, there is actually no network communication between the client and the server, and the accept and the connect actually establish a connection, an actual network connection, which allow the two processes on the two machines to communicate. Okay. Now that there is a duplex network TCP/IP connection between the client and the server, you can essentially use standard read and write calls to communicate. So you can write to a socket, the client can write an HTTP message to a socket, and then it will get sent to the server, and the server can then read from its socket to receive that message, and then it can send a reply by writing to its socket, and then the reply is going to go sent back to the client. So you will see that there are multiple reads and writes that will occur that allow you to have duplex communication, and eventually once you're done with this communication, you can just close the socket descriptor. Okay. Now while read and write are standard calls that are used to read or write from sockets, you can also use send and receive that implement equivalent functionality. So send is the equivalent of write and receive is the equivalent of read. All of these are blocking calls, which means that if you read from a socket but there has been no network data that has been received from the other end, you are going to block until you actually get a packet. Similarly, when you write, you are going to wait until the write returns. In this case, the write is going to write to an OS buffer, and then it's going to return, just as file system writes write to OS buffer cache and return, and then the data is going to be sent over the Ethernet interface at a later time. So keep this picture in mind. Now this slide actually summarizes the POSIX socket calls that we just encountered. I'm going to go through them quickly again. So the socket call is used to establish an endpoint. Binds that endpoint to a local address, which is the port number, as I mentioned. The IP address is already determined for the machine. It's the port number that you bind to. Listen announces your willingness to start accepting network packets, and then accept basically actually establishes a connection by blocking until a client connects to the server. And then connect is used at the client end to connect to a server that is accepting connections using accept. And then you use send and receive, which are, as I said, equivalent to read and write to send and receive data, and closes the connection. Okay. So this is a POSIX interface that is defined by BSD sockets. Any OS that implements socket communication and adheres to the POSIX standard has to implement these functions. Typically, they will be system calls in many OS kernels, but in some cases, they may be library calls that are implemented over other system calls. Okay. So with that socket background, let's now look at how socket communication, TCP/IP, and the data link layer are implemented in the Linux context, and then I'm going to switch to the Minix context. So the next remaining time in this lecture, we are going to essentially first look at Linux, and then we are going to look at Minix. So this picture here on this slide shows us how socket communication works, and it also relates the communication within the Linux kernel to file communication. So to your left, you see the file path, access path, and to the right, you see the socket access path. So if you are reading or writing to a file, your read or write requests are going to arrive at the VFS layer, and the VFS layer might actually hand that to the file system if you have a local file system such as ext4, or it could hand it to a network file system if you have things like NFS or Samba drives or iSCSI, which allow you to read or write files from a server. Okay, so the VFS layer can handle both network file system and the ext file system. Now, if the VFS layer is actually dealing with a network file system or network storage, that communication has to actually come back to the network path, because those packets are going to go over the Ethernet driver to a different machine. But if the VFS communication goes to the local disk or a local file system, then it just goes directly to the disk driver or the file system and the disk driver. So there are two paths out of a VFS layer, depending on whether you are reading or writing to a local disk or a network drive or a network file system. So now looking on the socket access path, when you read or write to a socket, it's first going to arrive to the protocol families layer. This is somewhat similar to the VFS layer, where you can have more than one protocol families be plugged into it. Just as the VFS layer allows you to plug in multiple file systems, here you can have more than one protocol families. Typically, most Unix-like file systems will support at least two: INET, which is the internet protocol or the TCP IP protocol, and Unix sockets, which I'll come to in just a moment. Okay. And then you're going to go to the actual implementation, the protocols itself. So say that you're trying to send this packet over or using the INET protocol family. So that packet is going to be sent to the protocol box that is shown there, where you have the transport layers, use TCP and UDP, as well as the IP layers. And then once it's being processed by those two layers, you are going to send it over the network interface. And you can have different network interfaces such as Ethernet, which is 802.11, and Wi-Fi, which is shown here as 802. Ethernet is 802.3, and Wi-Fi, which is shown as 802.11. So once you give it to the network interface card, it's going to get sent out over the network channel using the device driver. So I'm now going to look at the socket access path, and we'll look a little bit about in more detail on the protocol families and the protocols and network interfaces themselves. But let's start with the sockets interface. Okay? How is that implemented in the Linux kernel? So essentially, Linux implements system calls like socket, connect, accept, all of the ones that I mentioned earlier. They all implement the POSIX interface, which is somewhat independent of the protocol itself. The POSIX interface is standardized so that it's not directly dependent on TCP/IP. In the future, you might have other protocols that use the same standard. At least in Unix, you also have something called a Unix domain protocol, where you can communicate internally without using the network stack, using Unix domain sockets, which are what processes can use to send or receive messages to one another. So local send and receive use Unix domain sockets, whereas network sends and receive use networking sockets. So both of those can be supported using the POSIX socket interface. So you will see that the main call within Unix is called syssocket, which is the implementation of socket, and essentially you have a handler table which is going to track all the open sockets, and then once you decide which endpoint this is for, you essentially call the right handler. Okay? And there are lower level functions that are supported here, which are such as socket create, socket deletes, and so on. Okay? So that's the socket layer within the Linux kernel. Now the next layer down, if you go back, we're just going down the socket access path. So we just looked at the socket access. So the next layer down is essentially the protocol families. Okay? So essentially this layer is, as I said, analogous to the VFS layer in the file system. This is the layer that allows you to implement multiple protocol families. The two that are implemented are essentially the INET family, which allows you to do TCP/IP communication, and the Unix family, which allows you to use sockets for inter-process communication within the machine rather than using the network communication across machines. Okay? Now this is extensible through implementation of modules and function pointers. So the interface allows you to plug in a new module that implements a new family, and there are function pointers that you can use to instantiate the interfaces of that protocol family. And there are calls like create that allow you to initialize a particular family when you boot up the machine. So let's say that the socket call has come to the protocol family layer and you are using TCP/IP communication. So it is going to get it is going to invoke the INET family specifically within the protocol families. So the INET family can itself support multiple protocols. So you can have multiple families of protocol. Within each family you can have multiple protocol. In INET specifically we have an implementation of both TCP, which is our transport layer protocol that does reliable communication, and UDP, which is also a transport layer protocol, but it does unreliable communication. Right? Now, as is shown here, you have essentially the two boxes that are shown here are boxes that implement the TCP functions and the UDP functions. And these protocol functions are stored in something called proto-ops, with the protocol operations. And there are many operations such as bind and listen and connect and so on. And you see that in the stream ops which implement TCP, there's an INET bind that implements TCP/IP bind, and INET listen that implements listen for TCP, and connect that implements connect and so on. Okay. And the lower box which shows you INET dgram ops, which stands for datagram operations, implement the UDP. And you will see that not all functions need to be instantiated in each protocol. For example, because there is no end-to-end communication or establishment of a channel between the sender and the receiver in UDP, the listen call is null. You will see that. So not all functions have to be implemented. It depends on the protocol family. Conversely, if the same code can implement certain functions, you can also share it across protocol families. So INET bind, for example, you will see is the same in both cases. So you use the same function to implement the bind function. But connects are different for TCP and UDP. They have their own implementation within each protocol. Okay. So now let's talk a little bit about how packets are created and sent and so on. So you have essentially the TCP send message function, which is used to send a TCP message. It uses a socket buffer data structure. So your network packet is essentially copied into a socket buffer, and then you essentially send it to the TCP transmit function, which is then going to essentially send it over to or put it on a queue for transmission. Okay, so the socket buffer data structure is key to implementation of this of the socket abstraction, and that buffer is used by TCP and IP and so on, and sent all the way down to the network header. So that's a memory buffer that is essentially processed to the protocol stack as the packet gets processed through multiple layers. Now, because you have to essentially decide where to send this packet using IP, which is the network layer that implements routing, there are additional functions that are implemented within IP that have to do with fragmentation as well as routing. Okay? So what's fragmentation? So suppose that you wanted to send a large message from one machine to the other over the network. Typically, the TCP/IP protocol is going to have a maximum packet size that it's willing to use for sending packets out. So if your message is larger than the max packet size, the message is going to be chopped up into smaller packets, each of which is of the max size, and then it's going to be sent over. And that process is called fragmentation, where you take a larger message, you partition it into smaller network packets and transmit them. At the other end, you have to do something called reassembly, where since you have to reconstruct the original message and they are received as independent packets, you have to take data from all of those packets and you have to reassemble the message. Okay. All of that is being done at the IP layer. So the IP layer is also responsible for fragmentation and reassembly of larger messages. It also does routing, as I mentioned. That's a key function of the IP layer. So routing simply involves looking at what is called a routing table and trying to figure out the best match for this packet based on the source address, the destination address, the source port number and the destination port number. The routing table is going to tell us what is the next node to send it to. Okay. So if you're a router, you received a packet, you look at this routing table and it tells you what's the next router. If you're a sender, you're going to essentially say what's the first node in the chain that I'm going to send this to. So all of that is being done through routing. And in the Linux kernel context, there are multiple tables you can look. One is the route cache, which allows you to actually look at recently cached entries and then find a match. If you cannot find a match in the cache, then you actually look at the routing table itself, which is which is called a FIB, forwarding information base. And if you still don't have it there, you are going to then use the slow routing path, which is you're going to look at what to do with the packet or send it to the default gateway and things of that sort. Okay. Now, once the IP layer has processed this packet, you are going to then send it over to the data link layer, which in our case is going to be Ethernet. Okay. Now, the way Ethernet driver actually works is it essentially has a circular buffer where it has queued packets for transmission, and then it is going to take the packet at the head of the buffer and send it out. So the buffer has a head and a tail. The IP layer is going to keep appending to the tail of the circular buffer, and the driver is going to take packets from the head of the buffer and start transmitting it. Okay. So this allows the buffer mechanism allows you to deal with speed mismatches, because the rate at which you can send may be different from the rate at which the user process is generating packets. So you just queue them in a buffer, and it's a circular buffer, which means it has a max size. So the packets are enqueued at the tail and dequeued from the head. So that's the basic concept, and what is shown here are some details of how Linux actually implements these functions. You will see in this picture there's a middle box which looks like a buffer, and that's the circular buffer I was talking about. So there is a device queue transmit function which takes a socket buffer and it enqueues it into this buffer. Okay. And then you will see that underneath, the lower part of the device driver is going to now take dequeue packets from the buffer and then actually use the start transmit or the start exmit function to actually start sending them out on your interface. Okay. Now, in this context, I should also mention that there are additional functions that Linux kernel supports which I have not shown here. So for example, you can do network packet scheduling. You can decide if there are different senders, different processes, how to schedule packets that are being sent across by different processes by allocating things like weights to each process that says that allocates network bandwidth to each process. So in that case, your buffer is no longer a simple FIFO buffer. Here in this picture, we are showing a FIFO buffer where there is no attempt at scheduling across processes. But if you have allocated things like weights and you're doing fair scheduling or lottery scheduling across processes, you might have virtual queues, one for each process or each socket, and then your packets go into your virtual queue, which might be multiplexed or made to look like a logical queue, and then you are going to decide based on lottery scheduling or other mechanisms like fair scheduling which queue to dequeue from, and that's the that processes packet gets sent out next. So those functions are also implemented in the Linux kernel, but not shown in this simplified picture, which is the default way where you just use a simple FIFO queue or a FIFO scheduler to send out packets. Okay. So with that background on Linux, I'm going to start switching to Minix, and before I do that, I just wanted to tell you all a little bit about some high-level networking commands that you can use to manipulate network interfaces and so on. Okay. So first, for every machine, or we are going to assume that there is a link and a network interface, which could either be an Ethernet interface or a Wi-Fi interface. In all cases, the interface actually has an address called a MAC address, and it's a hex string that is shown, an example of which is shown here. So each Ethernet card will have a unique MAC address, or each Wi-Fi card will have a unique MAC address that allows it to essentially that is used for communication over a wireless LAN or a wired LAN. Okay. The addresses have to be unique, just as IP addresses, publicly routable IP addresses have to be unique. Ethernet addresses also have to be unique. So when you buy a machine which has an Ethernet card, the vendor has already pre-decided the Ethernet address. Okay. IP addresses are assigned when the machine boots up, but Ethernet addresses are hard-coded by the manufacturer on the Ethernet card. Okay. And IP addresses are also shown here as examples. You could have a 192 address, which is a private IP address. It is used in a NAT environment where you have maybe a home router. So you will have either a 192 address or a 10 dot address. Those addresses are private, which means they are only unique to your network but not unique globally. Okay. Publicly routable addresses such as 128, 119, 242 that are shown here, they have to be unique across the world, which means there can be only one machine that has that address. But private addresses can be reused within a LAN. You cannot use them to route over the internet, but they can be used within a LAN for communication. Okay. Now, with that quick background on MAC addresses and IP addresses, a few commands that you can try is, one is the ping command that allows you say ping and you specify an IP address that allows you to, that sends a packet to the other machine and sees if the machine is up. And typically if the ping is enabled on the other machine, you are going to get a response and also measure the round trip time for your packet to go from the sender to the receiver. Okay. If config is an administrative command that is used to assign IP addresses. First, it's to IP addresses to Ethernet drivers and Ethernet cards, as well as configure other details of the card, including whether the interface is up or down and things of that sort. Okay. And the netstat and the route commands are used more in the Linux context rather than the Minix context to either set routing tables or view routing table. So if you do netstat -rn on any Linux machine or even on a Mac, you are essentially going to see the routing table that is actually being used. So at the bottom, the picture on this slide actually shows you an example of a routing table on an Ubuntu machine. And so you will see that there is something called a gateway. That's basically the next hop. If the destination is set to 0.0.0.0, that's not a real IP address. That simply means that any packet that needs to go out, which is essentially represented as a string of zeros, are going to get sent to the gateway node, which is the next router in the path between that client machine and wherever else you're trying to send that packet. And you will see that's also associated with the interface ETH0, which is the Ethernet card on that machine and so on. So you can use netstat -rn to examine the current routing tables. You can manipulate the routing tables manually using things like route or other networking utilities. Typically when you boot up, these Ethernet interfaces are initialized. You might use either a statically specified IP address or use DHCP to fetch an IP address and assign it to an interface and then set the routing table. So typically all of that is done by the OS when you boot up, but a system administrator or a user can make these modifications to the routing tables and interfaces as well. So with that background, let's now move on to Minix. And the TCP/IP protocol within Minix is implemented as a system process, not surprisingly, unlike all other system processes. This one is called the INET process. Just as VFS was the file server process and PM was process manager, INET essentially implements the internet protocols, which is the TCP/IP family. Okay. The code for this server process can be found in the server's INET directory, and it collectively implements the Ethernet layer, the IP layer, and the TCP/IP layers. With one caveat, because the Ethernet card is actually an I/O device, the device driver for the Ethernet card is going to be found in the devices directory. Okay. So depending on how many, you will need one driver for a card, and there are many different hardware vendors for cards. So you might have multiple Ethernet drivers sitting in the drivers directory. The INET server itself is going to use more generic abstractions to communicate with any Ethernet card, independent of what manufacturer or what device driver is actually being used. So the code for the Ethernet driver, or the Ethernet layer rather, is split between INET and the device drivers, but the IP, TCP and UDP code all sit within the INET directory. Okay. And so the code can be found both in INET and INET/generic directories, and I'm going to show you a little bit of the details, but I encourage you to go and look at this code at the Minix subtree. Okay. At the bottom of this slide is a URL for a web page where there is an annotated version of some of the files that are found in the INET directory, with one caveat: those annotations are for Minix version 2, not version 3. There have been some changes between version 2 and version 3 as far as networking code is concerned, but a lot of the details in that are shown in that annotated web page are still true. So they're still going to apply to Minix version 3, which is what we are using in this course. Okay. So let's start with the data link layer. Okay. So the data link layer can use any kind of hardware for communication. That includes things like Ethernet, modem, Wi-Fi cards, as well as other cards. So you can use any of these interfaces to communicate. Each of them will have their own device drivers, and within each of those types of interfaces, you could have cards from different vendors, and each vendor has to there has to be a driver for each vendor's interface. Okay. So to do this, and furthermore, a particular machine might have more than one card installed on it. So for example, your laptop could have both a wired interface as well as a Wi-Fi chip that implements a wireless interface, and both of those could also be active. And so the way this is handled is you basically use the device major number and minor number. So the major number specifies the class of the device, which in this case are data link layer devices. The minor number identifies which specific card it is, if you have more than one card on your machine. Okay. And the data link layer is going to use the IO control or the ioctl calls when you initialize the card to set various parameters such as communication speed and so on. Okay. Now keep in mind that the drivers in Minix run as user processes separate from other system processes. So our Ethernet driver is going to run as a separate user process, separate from the INET driver itself. Okay. And all of the concepts that I talked about 2 or 3 classes ago, where you had a server process and the device driver and the VFS process that all communicate, still holds in this case. The Ethernet driver will run as its own process, the INET server will run as its own process, the VFS server runs as its own process, and they all coordinate with one another to send a network packet out, as we will see. So because this is a block driver, all of the concepts we talked about that concern with block driver also apply to this case. Okay. So let's delve into the code just a little bit. So within the INET directory, you are going to see inet.c source file, which is the main function for the INET server, and it is responsible for handling messages of various kinds that are going to come in. Like any other process, you are essentially going to have a main while loop where you are going to wait for a packet, rather a message, then process the message and send a reply. Okay. And some of the message types that are handled within INET are shown here. That's not an exhaustive list, but are shown here, which is open a device, close a device, do an IO control on the device, read and write to the device, and so on. Okay. Now within Minix, both the Ethernet card which is an actual hardware device, as well as the TCP/IP protocols are essentially accessed through a device interface, as we will see in just a moment. Okay. Now the INET server is also going to receive messages from the VFS process. And the reason for this is because we are using a /dev interface, which is a file interface for communication. If you read or write to a device using a file abstraction, those packets are first going to come to the VFS layer and then get handed over to the INET server. The INET server, of course, has to also talk to the data link layer, which is shown here as DL/Ethernet card. Okay. So that's the main function. There are several other files in that directory that are noteworthy. The buff.c file is responsible for buffering code that is for sending and receiving network packets. Okay. There is the Minix Ethernet code, which is the generic code for sending or receiving over an Ethernet card. And that code is going to interface with the device driver that actually does the sending or receiving. Okay, so this is the device independent Ethernet code that's in the INET server, and then the device specific one is going to be in the device driver. Okay. INET_config.c allows us to configure various networking devices, and you will see in this file, if you go and look at some of the comments, you see that it has code to initialize /dev/eth, that's the Ethernet device, /dev/IP, which is not a real device, it's the IP protocol, but you access it through the /dev/IP mechanism. You have /dev/TCP, /dev/UDP, those implement the UDP and TCP protocol. So we are using within the Minix OS, we are using these abstractions also to enable communication with through protocols. Okay. The MQ.c is the message queue structure. So that's essentially a network packet that we are going to create, and you essentially have a list of packets that is being tracked by MQ list data structure, and MQ type is one message entry, which is essentially a network packet that we are going to use for communication. Okay. Now, the interfacing with the file system and the VFS layer is all being done through one file, which is sr.c. And here you will see calls such as dev open, dev close, dev read, dev write that I talked about earlier are actually implemented. Okay. And then you have code for the UDP protocol and the TCP protocol that are essentially stored in the generic UDP.c and the generic TCP.c. And what I have not mentioned here is there's also a file called IP.c, which implements code for the IP protocol. So the transport layer is in UDP.c and TCP.c for UDP and TCP respectively, and the network layer is implemented in IP.c, which implements the network layer protocol. So with that was a quick run through of some networking concepts within Unix, how they're implemented in Linux, and how they're implemented in Minix. So that completes the very quick overview of the network subsystem. Again, I provided pointers to specific files as well as other URLs, and I encourage you to go and look at those resources to understand this in a little more detail. Okay. So let's stop here today. And starting next time, we are going to essentially switch gears and start doing more of a deep dive into the Linux kernel, so we understand how some of these concepts actually are implemented in the Linux context.